let's discuss more about eavesdropper detection. In classical communication, the data transmitted, which is say encoded either in laser's intensity or say its phase, this can be copied perfectly bit by bit. But in quantum mechanics, the no cloning theorem states that it is physically impossible to make an exact copy of an unknown quantum state, which means that if an eavesdropper tries to intercept the qubits and tries to copy the qubits, she cannot be copying them without disturbing them. And that disturbance is detectable by the legitimate users, which are at the end nodes. So with that, I would like to pass it to Matt to expand more on eavesdropper detection further and other post-processing steps.
Thanks, Suparna. Yeah, so in the case that an attacker potentially tries to disturb the quantum states, the resulting interference with those entangled photons results in some noise that appears in the measurements obtained by Alice and Bob. So even if they choose the same basis for measuring these photons, if the eavesdropper is now injecting new photons or manipulating them in some way, they'll find that now, even though when they're measuring in the same basis, they'll start getting differing measurement results. They might not necessarily be the same. And so in BBM92, we have a metric that is used to represent this called the quantum bit error rate, or QBER, and it's directly computed as the number of these kinds of errors over the total number of bits that we've collected by doing these measurements. So there might be some inherent noise in the system just because of physical imperfections when trying to realize these devices in real life. So there might be some electrostatic fields or temperature variations that disturb the state as it's propagating to the devices. But that noise is also affected by an eavesdropper, as we saw. And so if Alice and Bob have some sort of expectation on what that noise normally is, they can detect when higher levels of noise are introduced due to a potential adversary. And so now when Alice and Bob have collected their measurements, the way they identify the QBER on their secret measurements is by performing something called parameter estimation. And that is kind of depicted here in this slide. So Alice will first determine some subset of her secret key bits that she wants to use for parameter estimation. We can imagine that they're just sequenced in the order that maybe they were collected, and now she'll collect some indices that she wants to use for testing. So she'll select that subset of indices and ask Bob, hey, what were your measurements over these specific bits in that sequence? Bob will then respond with the actual measurement outcomes that he collected, and then Alice can now compare those measurements which she selected for testing with her own and obtain an estimate on what is the overall quantum bit error rate between the remainder of their secret key bits. So she'll then share this with Bob. And at this point, if this QBER is too high, it's beyond some sort of tolerance that they desire, whether that's above some expected amount of noise because of the physical system or some inherent threshold that they just don't want to try to generate keys above, they'll basically stop at that point, discard the secret key bits that they had, and try to do the process again on a new set of secret key bits. But if they find that the QBER is actually acceptable, it indicates that there's no eavesdropper on the line, then they can now proceed to actually post-processing those measurements further to actually extract secret keys.